Okay, so I am Matthew Reaney. I am a first-year PhD coming to the end of it. So what I'll be presenting today is sort of what I've been working on in my first year in cybersecurity with AI. So the goal of my research is basically to assess the viability of using AI techniques for network security. And in particular, I'm focusing on cyber-physical systems, and I've chosen an airplane or aircraft network for this. And the real motivation behind this is that modern networks they're really large nowadays, and they're very dynamic. And literature shows that some of the old rules-based techniques and other approaches are maybe getting a bit outdated, especially if you have AI-powered adversaries. So without further ado, if we can all make sure we've got our seatbelts on and stay seated during the duration of my talk. So I'm going to start very simple with some AI stuff, and to sort of give a bit of context to the problem of teaching things to AI. So we've all seen classifiers, or hopefully know the idea, but you basically train them on something to do a task. So for this, it's classifying fish. So we train it on fish, and then we test it on fish, and hopefully it says this is a fish. And then if we feed it something that's not a fish, it hopefully says this isn't a fish. So by looking at the accuracy alone, like something like this, we can say that works really well. But if we maybe put in something a bit more unconventional, or something new that comes along into our training or testing set, for example, that this image here of a fish, and we say, here we go, that's a fish. We can look sort of deeper than just your metrics or trusting this, and try and understand the behaviour. For this example, it's really trying to say that this is learning the water rather than the actual object. So behaviour is the real key, that you need to make sure that the AI is being taught the right behaviour, not just the right result. So my particular problem scenario, so I've collaborated with Rolls-Royce. It was going on a bit before I started, but I came onto the project and had various meetings about the various bits and pieces that would make up an aircraft network. So the first part we have is like a historian that's called the management, just logging all of the communications. And then we have an auto throttle, which is kind of like the brain or the calculator, taking in lots of data and then telling the computer, the plane what to do, speed up, slow down. And then we've got, no clue what that is, we've got the FADEC, which actually directly interfaces with the engine and does the control. And this communication between the FADEC and the auto throttle is really important. So that's the thing that we want to protect here in this scenario. We also have our blue team, or sort of our monitoring software that looks at the network, and to mirror that, we have an adversary. So they might be coming in via an external network link. Maybe there's Wi-Fi on the plane. More likely it would be the ground link of how the actual people who manage the airplane would get access to it. So the adversary's objective in our problem scenario is to disrupt this communication between the auto throttle and the FADEC. So there's no thrust information, no telling it to speed up and slow down. And the adversary goes through various steps of the MITRE framework, reconnaissance, privilege escalation, and we've got an 8-stage attack. And if they succeed and complete critical failure, well, it's no good for our scenario. So now we know what we want to train it to do, which is maintain normal operation of the network and the thrust value communication. So we can't just say it must stop this at all costs. It also needs to not stop how it normally functions. And the method that I've been looking into is reinforcement learning, particularly deep reinforcement learning, but I'm just going to explain the basic type. So it works in a loop, and the first component of that is the environment, which is sort of that problem scenario I just showed. and we've implemented it in a software called GNS3. So it's an emulation of all those components. So it's made up of various Linux systems, routers, we've got PLC for our controller, being maybe Debian systems. So they're all running in real time, and it takes maybe 30 seconds to a minute for the adversary to succeed. So it's maybe going a minute or two per scenario. And from this environment, we can observe things from it which we call states. So these make up various different things, like it might be our alerts, it might be the status of our computers turned on and off, or our systems on and off. And we also then want to quantify these. Is this a good thing that this is switched on? Is it bad that it's switched off? Are the alerts good? No. But we need to quantify that in some way, and we do that by defining a reward. And then our agent is basically our blue team in this scenario, acting as our defender. And they take actions, which is going to be like threat response, or what do you do? How do you fix the problem? And this action is then driven by your reward. The agent wants to maximize their reward to be as high as possible, rather than something like accuracy in the classifier I showed. This goes off reward. There isn't really an accuracy that you can use. So, as I said, you're going to use reward as your main metric, and ideally it starts off low. The first few times you train it on this scenario, it doesn't really know what it's doing, but it should figure it out, and then it'll learn that and then plateau. But we don't want to just look at reward. This is the same thing as just looking at accuracy. We want to understand the behaviour, and we can do this through a few different ways. So we can go deeper than just this. We also have all the state information I was talking about, and we can get insights from that of what the actual state of the network is, rather than just always trusting that the reward is high, so everything's perfect. And as I said, the behaviour, you can start to picture together once you gather all these things and look at the actions that the agent is actually taking to see, is this a good action to take? And for us looking in, it's often quite obvious. So, does it work? Well, my first example, we see the reward is quite low, and then it goes high. Now there's an anomaly in there. We all have those in our data, around 80. But it looks pretty good so far. But if we look at the alerts again, we go a wee bit deeper, and we can see, okay, there's a few alerts at the start, but they stop. So maybe it's solved the problems. Anomalies in this one too. If we go on and say, okay, well, what stage did the attack get to? Oh, it's still very high. It doesn't seem to have solved the problem. Well, what's the AI been doing? Oh, it's been blocking the connection to the security node. So it's been stopping all the security logs coming in. So essentially, in the event of a fire, it's turned the fire alarm off. So yeah. Another example here, to go through this quickly, gets a good reward. We go straight to the attack this time. Oh, it's starting to decrease. Maybe it's figured it out. Let's look at the number of computers turned on. That seems to have decreased a little. It's turned off our management. So the system's still working, but it's just turned off the historian. So this is better, but you're still disrupting the normal operation. You're gonna, have to go and look to see, well, what was it up to? All the information's not being stored anywhere. So yeah, does it work? Yes, eventually. So these are the results from my first publication through my PhD, and we can see it gets a bit better with the reward. The attacks are down. Well, look, is it turning things off that it shouldn't be? No, they're all still okay. Well, what's it doing? It's resetting the router that is the external network, gaining, or how you gain access from the external network. So it is, in doing that, resetting that, it puts the firewalls back up that the adversary's taken down during his attack, which has sort of stopped him from getting in and getting any further. So it does eventually come to a solution that is good. Takeaways from this, I hope I've sort of given you some insights here. of how I've created this, how the training works, and some of the challenges faced. And I'm only coming to the end of my first year, so there's a lot of future work to be done on this. Is this going to solve all problems? No. The first thing that comes to mind, this is one attack that it's trained against. I don't think there's only ever going to be one attack, and I'm sure you know that too. So there's lots more to be done that I'll be looking at. But that takes me to the close of my talk. So if you want to check out more about this, you can find my paper about it here, or I'm happy to speak about this later. I don't know, no time for questions. You'll have to find me later or read the paper. Okay, thank you very much, folks.